Additive manufacturing is a commonly used technique that allows us to produce highly complex parts while simultaneously reducing the cost, waste, and time to market of our printed components. Despite these advantages, there are still some key limitations with the process, mainly due to the fact that it's uncertain and highly variable. This leads to the formation of defects throughout the printing process, which can degrade the quality and usability of our printed parts. Because of this, there's been a big push in research to develop artificial intelligence-based models, primarily using machine learning and deep learning, to detect and identify these defects during the printing process. However, these models require large amounts of data, which can be very cost prohibitive, especially for small to medium-sized manufacturers. Because of this, there's been an interest in developing what we call collaborative data sharing frameworks, which allow a small collection of users to share their data to create a larger aggregate set of training samples. These training samples are more diverse and they allow for a more accurate and robust model to be developed. However, this framework does have two key limitations. The first of which are the major data privacy concerns that can arise when we're sharing our data outside of our organization. This is particularly the case when we're sharing AM thermal process data. This data is very informative of defects, but also contains embedded design features which can give away things like design attributes or key information about the overall design geometry, which can lead to things like re-identification attacks and ultimately the leakage of intellectual property. In addition to this, we also need to consider how can we effectively use this data. This is because the data itself is coming from a variety of different users in different applications. These different users have different equipment, different machines, different processes, and they even have different parts they're trying to print, all of which can lead to differences in how their data appears and how it's distributed. Because of this, we want to try to mitigate the misalignments in the data that might occur. If we don't, this data misalignment can lead to decreases in our model accuracy and degrade the overall usability of these models. My research aims to fill this gap by proposing a secure and effective way of sharing AM process data through a collective framework. In this framework, my research specifically targets, first, the de-identification. This is where we're trying to de-identify our data and ensure we can get a measurable level of data privacy while simultaneously ensuring our data is still usable. This allows our users to be able to safely and securely have peace of mind when sharing their data outside of their organization. On the other hand, once the data has been de-identified and shared, we can then work to make sure it can be effectively and efficiently used. This is due through knowledge alignment techniques, which allow us to extract key information from each individual user's domain and combine that data into a shared domain where we can more effectively and efficiently train our model to detect defects. Overall, this framework allows us to ensure that the users can have security and peace of mind while simultaneously guaranteeing they can use their data in a more effective manner. This allows them to enhance their overall quality assurance capabilities and the ability to identify defects during the printing process.